Hello friends, in this webcast we're going to talk about the problem solving strategies of angular impulse and momentum. When we heard the term angular, some of us or most of us doesn't try to attempt this problem because it's not clear. I think the most problem is that if you we're not understanding the problem. But here we're going to see how we can apply the angular impulse and momentum. It's mostly about understanding the problem, but angular impulse and momentum problems are same as any other problem, are often easier. So let's see what our learning objective is. So today we're going to develop a formula sheet for angular impulse and momentum. Then we're going to explain the application, how and when we should apply angular impulse and momentum concept in solving a dynamics problem, and we're gonna solve 3 problems step by step. So these 3 types of problems that we're gonna solve today should cover most of the problems that you have in your textbook. So the goal is that after we cover the video, you should be able to attempt all the problem and solve all the problem in your textbook or any problem on the textbook. So let's talk about the cheat sheet, our list of the formulas. First is angular momentum. It is the momentum that we know, mv, multiplied by the perpendicular distance of any point. So angular momentum of point O, it would be the distance, perpendicular distance of the direction of the angular momentum, which is from the axis or point O is d. So if you want to know more about how the theory, there is a theoretical derivation in separate webcast. Just look in our channel, you should find that. So there is other relationship that we may not have to use frequently in our problem solving, but it's always good to know this relationship. There is 2 of them. One is that summation of all the moment about point O is equal to the time rate of the angular momentum h. Another relationship which is important and good to know is that the resultant force F is equal to the rate of change of the particle's linear momentum, which is L, and L means mv. So linear momentum, change in linear momentum is the resultant force. The next equation that we need to know, which is important, is principle of angular impulse and momentum. So we know this is angular momentum. So the initial momentum, 1 means initial. So initial momentum about the point O plus the angular impulse, which is moment about the same point O during over a period of time from t1 to t2. This is equals to the final momentum, angular momentum of the same point O, and 2 represents the final. So this is the principle of angular impulse and momentum. The last equation that we have to know is that conservation of angular momentum. It's the same as the previous one. Only difference is that we don't have the impulse part. So there is no angular impulse, and we're going to talk about how we know there is no angular impulse and when to use this equation and when to use conservation of equation. So let's move on. And always we may have to use concept that we have learned in previous chapters. So when we talk about the boundary condition for this session, angular momentum and impulse, there is simple particle at rest. If you know that our particle was at rest and then some impulse was applied or the radial distance was changed, so at rest the angular momentum would be 0. And for this particular chapter, to solve the problem in your textbook, you may have to refresh your knowledge about moment, torque, and a couple of moments. So torque. So torque, moment, and couple. Just refresh your knowledge from your statics. So let's talk about the application, where and when we can apply this angular momentum, impulse, and momentum. So the first application is simple. If the problem asks determine angular momentum, it's for sure that you're going to apply this angular momentum equation. So this is very simple. The second one is that if the problem includes circular, semicircular, or curvilinear path, this is a sign that is angular motion. So if it includes any of those, addition, so plus this, any of those, plus change in velocity. So again, 2-point velocity scenario, the velocity of 1 at the beginning is given, and there is another velocity 2 after a certain amount of time. So remember, there is time have to be included, and finally you have a force or moment or torque. So this is on top of that, and so in addition to the time, you will also have force, moment, or torque, because from this equation you have the dmv. So you have the radial distance and the velocity 1, and there is also velocity 2. So there has to be a change of velocity, and this moment, it could be given as a force. So you have to find the distance and multiply by that distance. I don't know, maybe x1 to get the moment. If the moment is given, you have to just directly plug into that, or if torque is given, this is also a form of moment, so you can just plug it here, and then you have to integrate. So we also need the time. So this is one scenario that if these are present, you know that, okay, now I have to use the principle of angular impulse and momentum. So there is a last scenario. If you see that your problem has this scenario, you also have to use the conservation of angular impulse and momentum. If your problem includes the circular, semicircular, curvilinear path, instead of there will also be a change in velocity, but instead of change in velocity of a time, after a certain time or given time, so there will be no time, but there will be a change in radial distance. So the radial change in distance could be, if you have a car rotating about a point, the radial distance is this d here, and after a second scenario, after something, or after a certain amount of time, if it changes to a new radial distance d2, so it also can cause the change in velocity, because your angular momentum is depends on d, this radial distance, and mv. So if d changes, your h will also change. So that will give us a new velocity. And also there should not be mention of any force or momentum or torque. So this will not be given, and only this change in velocity and change in radial distance will be given. So in this scenario, you have to use the conservation of angular momentum, so which is the momentum about point O initial, and then will be equals to the momentum about the same angular momentum about the same point O, which will be the final. So since there is no angular impulse, so this will be your equation. So these are the three scenario. If you see this three scenario, you have to apply these equations. So let's move on and solve three problems. So let's look at the first problem. First problem is pretty straightforward. we have a rectangular coordinate. There is a particle A here that is moving along this direction at 4 feet per second. It's if you extend the line, it's gonna touch the y-axis at point B. The dimensions are given, and we're looking, and the weight of the particle is also given, and we're looking for the find angular momentum. So this is the first check. We told if the question asks find angular momentum, we have to use this. So this is our definition. The first step is to write the definition of angular momentum. So we write h about point O, because the question asks to find the angular momentum about point O, and we know by definition we need to the radial distance, cross product, mass of the particle, and the velocity. And the weight of the particle is 6 pounds. So the first step would be finding the perpendicular distance, which is r. So from point O to point A, we can have the perpendicular radial distance, which is OA. So it could be OA cross product MV vector, or since the direction is the same, we can also take this perpendicular distance OB cross product of mass into velocity. So there's two different ways to do it, and we'll do both of them, and you'll see which one is easier. So to apply any of this equation 1 or 2, we need to find the velocity VA in vector form. So to find that, we use velocity magnitude, which is given 4 feet per second. We need the unit vector, the direction of the velocity, which is A to B. So how do we find that? We find the radial vector of A to B, and then the magnitude of that radial vector. So that will give us the vector form of the velocity. And if we do that, if your point A is this, is negative 8, 8 and 12, if your point B coordinate is 0, 18, 0, if you do this math, you will get the velocity VA in this form. So this will be your result. So you can see that we have our VA. So I can use either of the equation. We know the mass, which is 6 pounds. All we don't know is ROA or ROB. So ROA is easy. Negative 8I plus 8J plus 12K. And ROB is even easier. ROB is just 18J. So now we have found ROA or ROB, so we can either do this, or so we have all the unknowns, so we can do it either of those way. So we have all the unknowns. If we just plug the value into our matrix form, so ROA cross product MVA IJK, and I just put the IJK term of the ROA and IJK term of the velocity. I just put the first term, it would be the same. So M into VAX, this is M into VAX. So 6 over 32.2, this is to convert from weight, 6 pound, to mass, and this is the x component of the velocity, and it will be the same second j component and k component. This part would be the same, you have to change this part. And same thing if you do on ROB, it will be the IJK. This line would be the ROB that we just showed you in a previous slide, 0, 18, 0. So you see there is more 0 on this one. So if you do ROB, it is much easier because most of them are cancelled out, and then this part is going to be same as this 3 term here. So in both way you can do this, and the answer will be negative 9.17i, negative 6.12. So this is our answer. So now we're gonna go to the second problem, but before that I would like you to pause and review the theory that we have covered, review the 3 scenario that we said that if you find those, and then you should apply this principle of angular impulse and momentum. So practice those, review your notes, take a break if you need, then move to the second problem that we're going to solve. And in the meantime, you are always welcome to take your textbook and attempt any problem. So let's move to the second problem. So let's see the example 2. The problem says that there is a car moving in a circular path in this direction. It has a force acting on it, which is 15 Newton. That means the force is dependent on time, and there is also a moment active, which is on the z-axis, which is 30 t square. That is also dependent of time. The car starts from rest, and the total weight of the car is 150 kilogram. The question asks find speed at t equals to 5 seconds. So before we attempt to solve the problem, now we're gonna check how this problem, we can determine how this problem is applicable to angular impulse and momentum. So when we check the problem, we see that the car is moving in a circular path, and it has a change in velocity after a time. So it is asking, it's a two-point velocity scenario. The velocity is given at the beginning, which is at rest. It is asking for the final velocity after a given time. So there is change in velocity, and there is also a moment and force given. So this suggests that we have to use the principle of angular impulse and momentum. So now let's move on and solve the problem. So to solve the problem, since we have determined that we have to use principle of angular impulse and momentum, I'll just write down the equation, which is h1, the first angular momentum, plus the angular impulse equals to final angular momentum. Since the body was at rest, so this becomes 0, the initial angular momentum, so I put 0. There was a moment active, so I just used the 30 t square, and dt remains the same. There was also a force active, so we use 15 t, and since a force, to make it moment, we have to multiply it by the radial distance r, which is given on the problem. So, and then this is the final part, which is mv, the linear momentum multiplied by the radial distance. So the mass is 150, and r is 4 feet given, so I just put it there. So if you just do the integration and solve, you'll get the velocity v equals to 3.33. So that is our answer. So we solved it. So next we're gonna do example 3, but again you can take a break and review the notes again, listen to your best music or so, attempt any problem given in the book, and you can come back for the example 3. So this was example 2. We'll do the example 3 now. So the problem 3 says there is a car again rotating in a circular path from point O. The radial distance and current scenario is 8 meter, and the car has 200 kilogram. So this OA, the car is rotating about, is connected with point O with a cord OA. So from here to here, this OA is being pulled. So the car will be here after some time, because this OA is being pulled in that direction. into the hole. So the OA is being pulled at 5.5 meter per second. Start from t equals to 0. Find speed of the car, of this car, at t equals to 4 seconds, and find also the work done that take to pull the cord. So first we're gonna do the checking. First check is that this is a circular motion. Fine. There is also a change in velocity because it starts from rest. The car, when the radial distance is 8, the car has a velocity given which is 3 meter per second. And what is the final velocity after 4 seconds? So check, it is a circular motion, that there is change in velocity, and also there is a change in radius. This is the important thing. Since the OA is being pulled, so our R8 will be changing because this OA is changing. So this is the radial distance changing. And radial distance change is also changing the velocity. So this is not an impulse. There is no impulse here. There is no moment or force given. So we know that we have to. This is the third scenario where we have to use the conservation of angular momentum, HO1 equals to HO2. So now we have figured out that this is not the principle of angular impulse and momentum problem, but this is just a conservation of angular momentum scenario because it's just changing in radius and there is no force or moment given. So let's solve the problem. So to solve the problem, since we know that we have to use conservation of angular momentum, I just write the equation. That's my first step. Now I simplify the equation writing what is the angular momentum, mass, velocity, and radial distance r. Final for the two radial distance, new radial distance, because the radial distance OA is changing, and then mass is the same. What is the final velocity? So what do I know? What do you don't know? We know V1, which is given, which is 3 meter per second, which is all given in the problem. We know the R1 at the beginning, which is 8 meter. We don't know R2, we don't know V2. V2 we're looking for, so we need to find R2. How do we find R2? This is our second step. To find R2, it says that the OA is being pulled at 0.5 meter per second. So 8 was the beginning minus 0.5 into 4 seconds because it was moved for 4 seconds. So we found 6 meter. So R2 is 6 meter. So if we plug back all those value, R2 here now, if we put R2 equals to 6 meter, so you know R1, V1, M is 150, and it can also cancel out from both sides. So you can find V2, which is 4 meter per second. Now you might think this is our answer, but we have to consider that this is the radial velocity of the car, 4 meter per second. Now in this scenario, when the OA is being pulled at 0.5 meter per second, to find the speed we have to do this an additional step. So the normal component of the velocity 0.5 being pulled, and then the radial the tangential component 4 that we just found out here. So finally we'll get the velocity, which is 4.03 meter per second. So this is our answer, first part. The second part says what is the energy needed to pull the cord in this direction. So this is simple. If we just do work and energy equation, this is third step. We know this from our previous chapter. T1, the kinetic velocity of the initial position, plus work done equals the final velocity, final kinetic energy. So it's this half mv square, v1 square. So you know the value v1, and then you know the final v2. So you can find vu1 too, which would be 7.25 joule. So we have solved the third problem. Now you should be able, if you go to your textbook, there should be 3 different types of problem and that should fall this 3 scenario. Now I skipped this step when we solve the problem. Now you should pause and go do all the steps and make a clear note, and on the side make the decision that we made. It will be helpful for you to remember and understand. So that was it for today. Thank you so much. See you in next lecture. Till then, bye.